half an hour ago, I changed the order of today's presentation, bringing up what I think is, of all these very important lectures, perhaps the most important, as a first one, while you are still sort of awake and fresh in mind. And it's to make the point, to address it in a concrete way, I take a case from, to start with, from the 1930s California, where the first private weather firm by Irving Crick, a very controversial person in American meteorological history. And he was competing with the official Met Service called the US Weather Bureau. And I don't know exactly the climate of California, so the numbers here are just sort of pedagogical to illustrate the whole idea. The 30% of some bad weather, whatever, bad weather for certain people. The same applies, of course, for other percentages, but it might be less clear in the diagrams or pedagogically. And first, some theory. So one frequent objection or question from customers is, what shall I do with the probability I get? And in the first, so what I tell you now is a first approximation, and many of you I think have heard it before, and I tell it again because later, in the next 1.5 hours later, I will show that life is slightly more complicated. But we start with this basic notion that if you don't do anything, you will suffer a loss 30% of the time, 10 days out of 10 days in a month. And if the loss is L for loss, then your daily average loss will be P, 30%, times the loss. That will be your day-by-day average loss. And then you can, of course, protect yourself buying insurance or doing something, and we assume that it's done on a day-by-day basis, and it costs C. And of course, it all makes sense if the cost is lower than the expected loss. So when the cost is lower than the expected loss, you take action. And when it's larger, you don't take action. And the break-even point is when the cost-loss ratio is identical to the climate. So that is where you can do either things. So that's the famous cost-loss ratio. If your personal, and this cost-loss is your personal profile. Different people have different costs and losses. And it defines the relation in this game or decision-making. If it's generally higher or lower than the given probability, they take or take not action. And that is one of the advantages with probability forecasting, that different people can react differently to the same information. The disadvantage with deterministic forecasting, it will rain, is that it more or less the forecaster tells all the customers what they should do. But now they can make an individual choice. So we now, to bring in some simple mathematics, state that the typical loss is 100 euros. Fredrik, can you fix me a glass of water? And we deal now with people with cost from 0 up to 100. where the cost is equally as the loss. And we now, to come back to California, assume that the Weather Bureau is fairly skillful forecasting weather. So here is the forecast matrix. It tells, first of all, that over 100 days, the Weather Bureau forecast rain. Let's say rain is the issue, 30 days out of 100. So the forecasts are well tuned with climate. They are not all perfect, but 80%, 20 plus 60 are perfect. Of course, more when it's dry, because of course that is easier to forecast. So I think this is a typical forecast map, forecast verification table. And then this is another way, because when you forecast rain and it occurs, it's called a hit. And when it doesn't verify, it's a false alarm. When you forecast dry and it rains, it's a missed event. Then you have this neutral. And here is the decision matrix. So whenever rain is forecasted, you take action if you think it's your advantage. Or if you don't, you run the risk of being hit by a loss because of the missed event. So the expected monetary value is a weighted average of the number of cases you protect and the number of cases you are hit by losses. So actions are taken when it's rain and no action, and you run the risk of losing. So here is now when you never protect, you run, as I said, an average risk of 30%. So you will lose on average 30 euros or dollars. Now this is euro, which was not the currency in California in the 1930s, but never mind. So 30 euros per day on average if you don't protect. If you protect, depending on your cost, it will be an increasing sum. So if you have no protection cost, of course it's zero, but then with increasing cost, the curve will rise. And there is a point where these two meet, and as I said before, it coincides with the climate. The cost loss 30 divided by 100 is identical to the climate of the region. So here it's good to take action for people with low cost. They take action because they can afford it. Whereas people with high protection cost are more favored by not taking action because that would be too expensive. It's better to take the chance of losing once a while. Now, even if the forecasts were perfect, there would still be money to be handed out. So this is a sort of the bottom line, the ideal line, when we have reached the stage where we make perfect forecasts. It will not be completely cost-free, of course. And this is now, this triangle is where the forecaster or the forecast come into picture. It's here where we can make a difference to advise people beyond the sort of climatological or average reaction or reactions without considering weather forecasts. And now the Weather Bureau, we can now with this forecast matrix, we can see where they come in. And here is now their typical curve. The cost for these people, the So the x-axis you can see as a lot of different people or companies or agencies with different cost loss. And from this curve you can see that those who have very cheap cost don't really bother about weather forecast. They might appreciate meteorologists, they might admire their skill or whatever, but actually they have so cheap cost of protection so they don't bother about the weather forecast. And the same applies for the other end, that they have no neglect of weather forecast, but it's just too expensive to take the forecast into account. It's only a fairly broad but limited segment of the public that has a monetary interest in the weather forecast. And it's good to know that people who don't use our forecast might not necessarily dislike us. It's just that it doesn't pay off. So this explains why this can happen. So this is now the gain. A large sector, but not the whole sector of society, makes from following the US Weather Bureau forecast. But now we come back to Crick. And he was an odd meteorologist because, as I read, he had sort of very strange forecast. To some customers, when there was a cloud on the sky, he warned about rain. And to other customers, even if the rain were dark and hang low, he might say, well, it will stay dry. And this was very odd. And if you followed and took statistics, you would see that his forecasts were not at all well tuned. So for one customer, he heavily over-forecasted rain. And for the other one, heavily under-forecasted rain. And of course, in comparison with the US Weather Bureau, he scored badly, or he would score badly in any verification competition. But still, he earned millions of dollars. And that's why he became controversial and sort of the Saddam Hussein of American meteorology. So why? And the reason was that he had two very special customers. The first one, the one to which he over-forecasted rain, was Hollywood. And when they were shooting their wild western movies in the 30s or whatever, out in the desert or prairie, they didn't want to do that if there was any risk of rain, because it was expensive with all the equipment and the movie stars and etc. So they want to be absolutely sure that it was fine weather out there. So that they had an interest in over-forecasting the rain. So when Crick said no rain, they could be damn sure it would not rain. The other customer was the water authorities in California. And here I'm not exactly, I have asked hydrologists in the HEPEX community why, and they are not quite sure, but obviously for reasons I'm not aware of, the water authorities in California wanted under-forecasting of rain. Perhaps they didn't want to spill out expensive, because if there is rain, it might sort of overflood, might cause problems, so they have to empty some of their dams. And if there then is no rain, they have emptied unnecessarily expensive water. That might be one reason, but anyhow, they liked under-forecasting of rain. And they got that and they were happy and they paid him. So these very special customers got very tweaked forecast and paid him well for that, so he was happy. Now if we now look at this, so here we have now the Hollywood forecast. Heavily over forecasting rain, so we have the same type of matrix as with the US Weather Bureau, and we can see the economic outturn. So here is now the Weather Bureau, and and here is now the line for Hollywood. And as you can see, obviously Hollywood counts among the low cost loss customers. So they benefited from having these forecasts instead of following just climate, or even worse, following the US Weather Bureau that would over forecast or under forecast rain from their perspective. So they gained from this. And then we go to the water authorities in California. Here is Hollywood, and here we have the water authorities. And again, they are in the higher cost-loss ratio, and they benefit from this forecast compared to the official or to the climate. So that was a secret behind why his sort of bad forecast gave him huge gains in money. So he is now his gain area, Crick's gain. And that also shows why sort of statistical verifications, which we must do, so it's nothing wrong with that, but they can only be seen as a statistical verification or validation of the forecast. The usefulness might not immediately or does rarely follow from these statistical verifications. So here is the US Weather Bureau still had a little sector of possible customers if in case Crick went public and issued these forecasts for the public as well. Now, the Weather Bureau could have, there are two ways for the Weather Bureau in the 1930s to combat Crick. And one was to invest in forecast development. There was still 15, 20 years for the computers to come. But even if there had been computers, improving the weather forecast along the lines that Cosmo does or UPSN, the Met Office, still takes time. It goes slowly, it's a steady progress, but it's not fast. And the Weather Bureau couldn't wait for 20 years. They had to find a quick fix. I don't know what they did. So what I tell now is if I can travel back in time to California in the 1930s and be employed by the Weather Service and advise them what to do. So what they could do quickly to beat Crick was to make use of a seemingly weak part of their skill, their uncertainty. So you assume now that the Weather Bureau in 40% of the cases were not quite sure. In 60% of the cases, mainly when it was dry, they were absolutely sure about the forecast. But assume that in 40% of the cases, they were not sure. And just to press the point, they would say, today we don't want to make a forecast. Of course, that is politically impossible, but now we are in sort of a fantasy world, so we assume that 40% of the time they refuse to make a forecast to the water authorities or Hollywood. That sounds bad, but it is good, as I will show you. Because, so I assume that when they are uncertain, there is a 50-50 chance of rain or no rain. I could also have taken other proportions, but I like persistence or climatology or pure guess, but I take this 50-50. So when they are uncertain, there's a 50-50 chance of rain or no rain. And they refuse to have any opinion. The point is now that depending on if they are, if the customer is Hollywood or the water authorities, they can interpret this sort of absence of forecast in different ways. So Hollywood, this is now let's see now, what am I? So this, I think, is the water authorities, if I'm not, yes. So one, yes, it's the water authorities. They interpret the absence of forecast that it will not rain. That is in their favor. So from this 2 times 3 matrix, they make their own decision matrix, yes and no matrix, where all these uncertain forecasts are counted as it will not rain. And then they take action from that. The other one, and this is now how this economy works for the water authorities. Or if it's, yes. So now I have confused. So this is now, the one customer interprets the absence of forecast in its favor. In this case, it's the water authorities that want under forecasting of rain. And here, yes, now the line is on the right place. So here is their curve, their expenses. And they, being in the high sector, gain by this interpretation. And secondly, and this must be Hollywood, they interpret the absence of forecast as it might rain. And then creates a decision matrix which is over forecasting rain. But it's their construction. And here is then their curve. And if we now combine these two as we did before with the crick, we can see that the gain, if now the US Weather Bureau wanted to compete with crick, they would win because their curve is slightly, their area, their gain area is slightly larger than crick. So all they have done, they have not invested into new observations or computers or what they have just, not even probabilities. They have just said, on certain days are we uncertain. Do what you want, which is not very recommendable, but in my scenario, that is what they have done. And that is enough to actually beat crick, to admit their uncertainty. And that, I think, is the key message I want to bring out. If you forget everything what I have said, at least remember this: to admit uncertainty in a clever way will actually be beneficial. And I will come back how to do that in a more diplomatic way than just make a walkover. And so admitting uncertainty and realizing it's not a way to cover our back, it's actually additional information that people will benefit from if they are wise. Now, this is now going back to this 40% of uncertain forecast. But of course, as most of you know who have done any forecasting, even if you haven't done forecasting, when you are uncertain, sometimes you are more or less uncertain. And that is another additional information, exactly how uncertain am I. So this is now, let's see. So this is a repeat of the decision matrix for those with low protection cost and the decision matrix for those with high protection cost. But as I said, not all forecasts are uncertain. And from this 40% uncertainty, we can quantify that in one way or the other. For example, by converting this into probabilities. It can be converted first into, if you like, I'm almost certain, I'm nearly certain, I'm rather uncertain, I'm very uncertain. That would be enough to further add information to the customer if he doesn't like numbers. Just telling, I'm almost certain, I'm rather certain, I'm rather uncertain, I'm very uncertain. Then, depending on who the customer is, he can choose to take action or not, depending on his risks. And the next step is, of course, to quantify that into probabilities. But as you know, understand, if it's probability or not is not that crucially important. The importance lies first in admitting uncertainty, then telling verbally or in other ways if you are very uncertain or very certain. And then the third step is the probabilities. So the whole thing doesn't hang on understanding probability theory or being a PhD in statistics. It's to appreciate the additional information of uncertainty in an uncertain world, so to speak. So they could have further swept the floor with Crick. They, just by admitting uncertainty and refused to make a forecast, already that was enough to beat Crick. But they could completely destroy him, so to say, if they now quantify the uncertainty. So now for different probability levels, different customers choose to take action or not action depending on their cost-loss ratio. So from this forecast, a range of customers take action or do not take action. And we will see how that pays off. Here is now the deterministic forecast from the US Weather Bureau. And here is for those 100% probabilities, those who really want to be certain. And then we take the 80%, that is their decision matrix or table. And here is their curve. And then we go on like that. For every new customer, they have their personal expense curve. Depending on who they are, they will pay off more or less. And if we now put it all together, then those with low cost loss, they follow forecast along the 20% division line, 40%, 60%, 80%. So they know which probability level they should watch out for. And then if we add it all, you see now that we have almost come halfway to perfect forecast, perfect deterministic forecast in this example. So, and remember again, the numbers are not necessary. Also words correctly interpreted would, I think, almost give the same gain to the customers. But of course, when you use words, they are not uniquely defined, so there is some uncertainty in that, so it might be slightly less beneficial, but still far more beneficial than Crick's forecast, and in particular the deterministic forecast that I showed you originally from the US Weather Bureau. So, and also another advantage is, which I haven't mentioned, now everybody can benefit from the weather forecast. With the deterministic approach, then, as I mentioned, those with very low cost don't bother about the weather forecast, nor do they with high protection cost. But now everybody will find that these forecasts are useful. So now the weather forecaster can serve the whole community. Yes, that's all. But we live in a world where what is the best interest? And I come to think about Galileo and the Vatican Church.
You start from the...
And because you all are familiar and with this history. And being not a Catholic, I have still gone around the last 50 years defending the Pope, Urban, I think, Urban the 6th or Urban the 8th.
Yeah.
Because even if he had believed that Galileo had a point, first of all, it was not proven because Newton's laws had not been discovered, and it was only when they found that the Earth was flattened at the poles that they had a proof that it was rotating. So even if Urban, the Pope, had thought that Galileo had a point, the problem for him and also for the cardinals was not that there were some sections in the Bible where the Son wrote, because these are not very central texts in the Bible. And the churches everywhere are fairly good at giving interpretations. So that was not a big problem about certain sentences in the Bible. The problem was the general public. Because it was not easy, not even for the Pope, but he might understand, but for normal people, that suddenly they are told that they are moving eastward with, in Italy, 250 meters per second without noticing it, and worse, 30 kilometers per second around the sun. Why didn't they fall off? They didn't know about the centrifugal force. That was 50, 100 years later, but everybody knows if you are on a carousel, you will fall off unless you hold on. So the problem was, even if the Pope thought that Galileo had a point, and the cardinals, how to bring this message out to people, which would say, "What, this is crazy." And then if it turns out that Galileo was wrong, because it was not proven, then of course it would be enormous loss of prestige for the church to have said something that everybody could realize is completely crazy, and then it turns out to be crazy. It would be a devastating blow to the Vatican Church. So I have full sympathy for Urban and the Vatican Church that they took a cautious line. And actually, why they then were nasty, unnecessarily nasty to Galileo, was because of the Swedes. The Swedes. Because in 1632, there was this war, 30-year war, and Sweden had entered. And it's normally told about as a war between Protestants and Catholics. But that's not quite true. Sweden was Protestant, but they were called on to join the fight by Cardinal Richelieu in France, because he was fighting Catholics, Austrian Catholics. So in all this big power game, Sweden had entered, and the Vatican in 1632, for unknown reasons, sided on Richelieu and Sweden. And then to defend themselves against Austrian Catholics, they had to be extra pure. And that's why they treat Galileo extra harsh, just to compensate for their alliance with Sweden. This is according to documents found 10 years ago in Prague. So what I want to say with this is that politics comes into decisions. So it's not all decided by science. Luckily now, the Pope or the President of Italy would not reason along these lines. And perhaps in 200 years, the authorities in Bologna will be more easily dealt with. But now they have to think about the voters, about the personal standing, and all this complicates the decision process. And that's why they also want a deterministic forecast from the forecast. It will rain, there will be an earthquake. Because if it doesn't happen, they can blame somebody. But being told there is a 10% probability of an earthquake, then they have to make the decision at 90% being wrong. Now I'm sort of leaping ahead of myself, but here is a picture that has an Italian, so I must have got that in Trent, but I can't remember when. It's about measurements, analysis, forecasting, presentation, and then decision. That is a school book, how we go from observations to decisions for the benefit of mankind. And one important thing is that if we now are forced to, for political reasons, to deliver deterministic forecast, it's very important because I had a quarrel on a WMO course with a Canadian, and it was a bit embarrassing. If you issue deterministic forecast for severe event, then you must over-forecast. You are bound to, if you want to serve your customer, you must over-forecast. And how much you over-forecast depends on the cost-loss of that customer. And as you saw with Hollywood, they had strong reasons to get heavily over-forecasted rain. That was in their benefit. But of course, probabilities would have served them better. And I say so because when it comes to verifying numerical models, computer models, should never over or under forecast anything. They should be a true model of the atmosphere. But a forecaster, and I will come back to that in other ways, must under or over forecasting if he's serving a particular customer. So that's why actually verification comparison between forecasters and computer models is a priori impossible. They are serving different interests. So it's impossible to compare a forecaster and a computer. So here we now have, for example, a customer with cost loss 40%. And of course, he's best served by probability forecast. But on the other hand, so he can take action when it's more than 40%. On the other hand, if the forecaster knows that, his cost loss approximately, he can do the over forecasting himself. So either the customer takes a probability and makes his own decision metrics, or the forecaster, knowing about the customer, takes a sort of decision for him by over forecasting from the start. But then, of course, some other customer will have it over forecasted in another way. So a sort of fix. If you are not allowed to give probabilities, over or under forecasting cleverly will serve the same purpose. And then you will also take the political responsibility. Then he or she can blame you. But at least you give objectively a very good information in line with this person's interest. I found this I'm part of the HEPEX, the Hydrological Ensemble Experiment Group. And they sent me a very funny investigation, which I'm not quite sure if it has any bearing, but I like this. It is about, again, America, and it's the Weather Bureau, and it's New York, and it's baseball. And in the 1890s, there was a weather forecast given to New York Times, first from the Weather Bureau, and from 1896 from a private forecast office. And the big thing in New York in the 1890s was their baseball team, New York Giants. So that was what everybody was thinking about, their winning or losing. It's like football in Italian or in Italy. And there's a paper you can find on the web, Tell All the Truth but Tell It Slant. Testimony on media bias. And I quote it because I think that similar things might be conducted in Italy. not baseball, but perhaps football. But at least it tells me something. I'm not quite sure what, but I will show what they found. So until May 96, the weather forecast in New York Times came from the US Weather Bureau. And after, it came from this private company. And here are the forecast matrices when the baseball team was playing away and when they were playing at home in New York. But I will not go through it. It just, if you want after this to make your own analysis. The important thing is that when the forecast came from the US Weather Bureau, and it was made sort of objectively, because it was for the New York area, the population in New York. Then rain was forecasted 1/3 of the time. And independent on if the game, if the team was playing in New York or far away, it was more or less only slightly over forecast, as rain forecast should be, because it's sort of some interest, rather forecast it once too much than once too little. So it was sort of a well-balanced forecast service from the US Weather Bureau. Then it was taken over by a private company, perhaps in association with New York Times itself. I'm not clear about that. But now it changed suddenly. So it was still 1/3 of the time rain forecast. But when the team was away, it was heavily over forecast. And when the team was playing in New York, and when everybody had interest in nice weather to go to the match, it was under forecast. And since it was naturally over forecast by 2 to 5%, scientifically, it means that it was over forecasted and under forecast with the same amount when this private company who had an interest in pleasing people, because people wanted the weather to be fine. So you come with a good message. And also perhaps to encourage people to go to the game. So here is sort of a documented evidence how meteorologists, for unknown reasons, give the public what the public wants. And I know that myself from my forecasting, if you have a summer situation with clouds everywhere over Sweden and rain showers, then it's a little ridge over Denmark that might move east and might give some improvements on the west coast of Sweden. We sort of mentioned that to give some lightning, to some encouragement to people, and it normally doesn't happen. So people become disappointed. But people, Anders, please tell me something nice. And if you just say no, it's hopeless, it will rain, then you also feel that you are blamed for the weather. So we are under, I think also in Italy, under pressure from the public to give them what they want. And if we don't do that, we are partly guilty to the bad weather. So that is a pressure that we should watch out with. The pressure from the public to give forecasts they would like. And here's sort of a documented evidence that that has happened. So it would be interesting to see if the same applies for Italian football matches, depending on if it's played. Now, then there is another interesting case. It was a storm in autumn 2013. And you know this Euro alarm map. Bologna is part of it. You are able to come in and give a little color. And now there was a storm coming in from the north, from England. And this was the Euro alarm map early in the morning. And I was very surprised because the storm would move from England over Denmark, southern Sweden, and then over the Baltic Sea to the Baltic states. And there were warnings in Sweden, northern Germany, and Holland, as expected. But Denmark looked rather relaxed. Even northern Jutland was green, which meant no problem at all. So I contacted my Danish friends, and there was a lot of debate. And it turned out to be an interesting example of what is a good forecast. Because what the Danes had done, so this would have been so I would, as a Danish forecaster, have put red. But the Danish colleagues said, well, we can't be sure it will be red everywhere. No, but the risk is high. So what happened in principle was that and then the Swedish Met Service were criticized for over-forecasting the storm. They have forecasted the storm for Gothenburg, which was not hit. On the other hand, the Danes were criticized for not having forecast the storm for Copenhagen, where Kastrup Airport had huge problems that day. And what seems to have happened is, again, a confusion between pure statistics and utility. So what guided the Danish Met Service in this case was to make a good forecast. And now we have wind variation. It can be either in time, that the wind varies in one location, or at a specific time the wind is different at different places, which is quite common when you have a rather turbulent storm. Now, if you now want to make a good forecast for the statisticians, for the verification, just a deterministic one, then you take some sort of average. That it will optimize your statistical skill. And that is what the Danes did. They want to make a good forecast. Whereas the Swedes, now I happen to be Swede, but it is not, I could have just fooled you and taken the other. So it's not, I'm not chauvinistic because, but anyhow, they said, well, this is a dangerous situation. It's better to warn too much than too little. And that is what they did, and of course, sometimes had complaints that they were over-forecasting. But the complaints of over-forecasting was, in the end, less fatal than the criticism for having missed, for example, the chaos at the Kastrup Copenhagen airport. So, but it shows that when we have a model which we want to verify, then the statistical approach is the only one we can apply to minimize or maximize different statistical parameters. But when we are making forecasts for the public, we must think about the utility, what it's good for. And this is a drastic example how that can lead to quite different forecasting. And here's another way to illustrate that. Here are in a Venn diagram or observed winds, 25 meters perhaps in some region, a small area of 25 meters per second, or time of 25 meters per second, and then 20 meters per second. And if you have now a model, a numerical model, then it should behave more or less like this. It is not perfect, so it will not, the red line, the red circle will not completely cover the black circle. That would be a perfect forecast. But the size of the circle should be the same as reality, but displaced. And also the same for the 25 meter. So here is how a numerical model should behave, being a balanced impression of the storm. But the forecaster serving society, he should, if he's not allowed to make probabilities, over-forecast these very strong winds to be sure not to miss anything, or almost not miss anything. And the same applies for the 25 meter. So different criterions apply to mathematical models, numerical models, and to actually operationally issued forecast. And that's why we cannot compare the performance of forecasters and models. It will either mean that we destroy the models so they also start to over-forecast things, or that we constrain the forecaster not to be as sort of well-tuned as a model. He can only be well-tuned if he is allowed to issue probability forecast. If he's not, then he necessarily has to over or under forecast different phenomena. And then comes, I think I mentioned that before, that the cost-loss equation is a very pedagogical one, and that is where we should start. But life is not as simple as the cost-loss ratio. And I told you this on Monday, and I think most of you would take the 700 euros in hand rather than the 80% chance of getting 1,000. Although, according to the cost-loss equation, you should take the first option. And of course, if you are paid by Carlo or Stefano every month, you have to choose gambling your salary or giving a lower amount straight in the hand. Then, of course, the first choice is the best one, if it's sort of a repeated event. But if it's just one-off, then, of course, the second one applies. So it sort of complicates this cost-loss discussion slightly. And then we can go further, because there's this Daniel Kahneman I mentioned yesterday, written this book about fast and slow thinking. He got the Nobel Prize in Economy in 2002. He's not an economist, he's a professor in psychology. But what he did was to show that a lot of how people react on the market is not mathematically rational. There's a lot of feelings and misunderstandings around, and we must take those into account and not create some sort of super intelligent, mathematically clever man who always makes the right mathematical decisions. And what he found, among other things, and what made him famous, was this called the prospect model. Let's see if I can point. So here we have, let's see now if, So here we have pleasure and pain, or prestige, something emotional, and then we have this sort of monetary x-axis. But everything is not decided by money. And what we found is that I should have had another curve with, let's see. Okay, so what we assume with the cost-loss is that there is a strict proportionality between losing money and feeling unhappy, and gaining money and feeling happy. But he found that that is not the case, and he did that by putting people under test, how they reacted, as in this case with the money. Would you rather to take 700 directly or play the 80% game? So he found that the curve is actually so here is to get 100 euros for sure would be a certain pleasure, of course. And then he gave them an alternative to have a 50% chance to win 200 euros. And some people accepted that bet, but 75 or whatever percent preferred the 100, the safe 100. And that can be sort of explained by that the pleasure of having 100 extra was not double. It was not worth the risk. So people were risk averse. They avoided risk in this case. They preferred the safe option. That is how people reacted in this test. On the other hand, at the other end, and you can see that this curve, it is not symmetric. This curve slopes down faster than the positive curve. So here we have losing 100 euros for sure. Of course, that is painful. But then, of course, 50% chance of losing 200. And then it turned out that people were prepared to gamble on that. It gave them a 50% chance to avoid any loss at all. So then you have the opposite. Why not try? I have a 50% chance to avoid any loss. And as I said, the cost-loss model assumes this relationship. And something else seems to be going on a slightly more. Then, of course, we can make this three-dimensional or adding some other factor. But already here, the picture is complicated. Then I tried yesterday, after a beer, to what are the consequences in the cost-loss in the methodological world. And I'm not sure I found the right answer because I had taken a beer, I was tired, so I invite you to have opinions. But I think that this means people on the 50%, if they protect, they lose something for sure. Because it's an they pay something to be protected, and they will lose that money. And if there is a 50% chance of avoiding a loss of 1,000, then if people are risk-seeking, they might, in this case, neglect the weather forecast and always protect or not protect. I'm not quite sure here. Then if you have the 80%, then they might protect. So it means that they should protect. Now I am uncertain because it's just through new ideas or fresh ideas. If they have a cost loss at 50%, they don't take action at 50%. They wait until 80%. That is my perhaps false interpretation of Kahneman's curve. So they should take action at 50, but they take action at 80 instead. Or 70, at least not at 50, but at a higher level. And then we can also see other combinations. But I think this has to be explored from Kahneman's model, what the consequences are for in the weather forecasting, which might explain some problems to make use of a probability forecast. People don't react as we think they should. And I know from the Met Office, they issue gale warnings or heavy or strong wind warnings for the Scottish Alps. And they are called 80% probability for heavy, strong winds. But at least during my time there, the warning was issued already at the 40% level. Because people should take action at the 40% level if they were keen to save their life. But people would not take 40% seriously. So that's why these 40% forecasts were called 80%, just to scare them up and keep them at home and thereby save their lives. But of course the verifications from the Met Office were awful. But they rather prefer to save people's life than to have a good statistics. And that might be a reflection of this Kahneman's law in the practice of the Met Office. But I think that there are more examples out there that show that when people react as we think, irrational. They are following Kahneman's curve.
So let me know that 50% is a sort of a magic ratio.
Well, the 50% is another problem. I will come back to that.
That example.
Yeah. Now, it's 11 o'clock, so it's time for...
We could have the break here.
Yes. Just a few minutes. We will later today, I hope, use Trento dice game. And it was introduced in a telephone conversation between me and Andrea in autumn 2005. Andrea organized a training course on statistics, and we discussed over the phone how we could have a game to illustrate. And then we came up with this idea, and it's a dice with 1 to 6 symbols of either sun or rain. Then there is first you have, here is from the course. You remember, Andrea? And what we do is that we have another die with all the, let's see if I got it. Yes, we have this one. And we throw that, and it sort of defines which probability, the probability of rain. And now let's say it's 67%, it comes up. Then we take the die with, what is it? 4 rain symbols and 2 sun symbols. That is 67% risk of rain. So we take one with, well, let's say, we take the one with 4 rain symbols and 2 sun symbols, and then people are asked to either buy an insurance, and if now there's rain, they will not lose anything, or not take an insurance, and if there's rain, they will lose a certain amount of money. So we played that, and we even invited the population of Trento. Not everybody came, I think it was just an old lady. But then it was become very popular, so it was taken over by the European Center, and Anna Gelli was playmaster for a long time, and then we made them bigger, so they could. And that was my wife's relatives in eastern Finland took Finnish wood and made big dice. Then there was an English artist in Norrköping in Sweden who colored them, and they are now at the European Center, and I think they are still playing with it on WMO courses at least, or training courses. And then in Trento we wrote on a whiteboard, but then at the European Center printed money with Marabuti's picture. We didn't. Dominique Marabuti, who was the director, he was sort of portrayed, but we don't have the money here, so it will be difficult to play exactly this game. But it was quite fun. But now it's time for coffee. So now I go to today's third presentation, and that is about communicating probabilities. And a lot of work is done in this field. There have been papers both in, as I know, in weather, in the European Meteorological Society's weather, and also in the methodological application, and I think also in American Met Society's weather and forecasting, where they investigate how people respond to forecasts expressed in different ways. But what I show now is my personal experiences and what I have seen in books, not necessarily related to meteorology, as Daniel Kahneman's Thinking Fast and Slow, so which I have sort of translated into meteorology from my own experience. And the probabilities are controversial for several reasons. And because, as I mentioned before, it leaves the decision to the decision maker where it actually belongs. But as has been scientifically investigated, the decision maker might have his own interest in avoiding responsibility and having somebody to blame. So there's a sort of a cost-loss ratio.
You can remove the might.
Sorry?
Remove might. The decision taker always has interest in removing responsibility.
Yes.
Not might have.
No. But okay. So sorry for being. And this is actually an authentic. This was said at a cocktail party at the European Center by a European director. I hope not the Italian one. I think it was a Danish. But that we want more accurate forecasts, not some bloody index telling how uncertain the forecasts are. And
because it's the same of my shift. I have to send him. He is not alone.
Te la puoi rivendere ai tuoi politici di Valerio.
I send it because I believe he is not.
But then we end up in a sort of very, what I like, sort of corruption. So here we have the blame game. It sort of gives this blame game, which is favorable for everybody except mankind. So you have the customer.
May I take 1 minute to tell a sort of an anecdote?
Yes.
Very many years ago, when we were trying to
Would you want this?
ensemble forecasting. Oh, it doesn't matter. I have because you want to.
You have to register.
Yeah,
Because it can be used against you.
I cannot tell names, but I'll tell the episodes. I was invited, it was I think an anniversary of the Florence flood. And
1966.
the 1966 flood, the very famous Florence flood. Could have been 96, 30 years or something like that. And I was invited to give this lecture to a very distinguished audience, mostly dominated by hydrologists and by people who make numerical models to, flood forecasting models. And so I spent almost an hour explaining what ensemble forecasting was, the problem of probabilities, and this terrible problem of trying to forecast the forecast skill. We were at those times in those days in which forecast spread was practically the only possible source of information about forecast skill in terms of the early ensemble forecasting. And at the end, the guy who had organized the whole thing, who was an experienced person, an acculturated person, not an ignorant person, said this was very interesting. He was commenting on my presentation. He said it's a very interesting presentation because we have seen how the progress in numerical modeling is going, where it is going, where it is bringing us. And I am confident that when the progress will bring us even further, not only we will be given with a possible variety of forecasts, but the forecasters will be able to tell us which one of those is the correct one.
Well,
30 years ago, 35 years ago. So things don't really evolve very much in people.
but this was.
Only one will be left.
But this was not a meteorologist.
Sorry?
It was not a meteorologist.
It was a very acculturated hydrologist.
Hydrologist, yes. But I can sort of beat you on this because I have a very accomplished meteorologist, the director for the German Met Service, who, as in his capacity as president of the ECWF, in 1999 or 2000, when we had this 25-year celebration, in front of the whole audience, expressed exactly the same thing. He appreciated the advance of the European Centre, research, etc., and he set a goal for the future to tell us which one of the members would verify. And nobody reacted, because perhaps they all thought the same thing. It was only I, oh dear. At the same time, because Germany was a sort of real devil's den when it came to probability forecast. West Germany. The East Germans, thanks to perhaps influences from Russian statistical traditions, were quite normal, open-minded and good. So I had about the same time a visit by a German meteorologist, and I showed him the Metos room and the probability maps, and the Germans are very self-confident. So whereas other people kept their ideas for themselves, the Germans were confident to express them. So he said, well, probability forecasting is nothing for German forecasters. It's for Italians who can't make up their mind. And that was the darkest hour in my. But then something.
I like the idea of
Then something good happened, because in the finance ministry in Berlin, they heard rumors that good German D-mark, this was before the euro, was spent on some idiotic project in England called Ensemble Forecasting and Probabilities. So they sent a delegation to IdroMeteoClima to find out what was going on. And Tim Palmer and Dave Burridge were nervous, but I said, no, it might work out because they are not German meteorologists. And rightly, this delegation obviously also had good contact with the Bank of England, which actually had been inspired. The Bank of England had been inspired by the European Centre to present their forecast of the pound or the different indices of the economy with great uncertainties. And also the head of the Bank of England, he was a member of the Royal Meteorological Society, and he even had a meeting presenting his ideas how the Bank of England had learned from IdroMeteoClima. So this German delegation for the finance department in Berlin came in very good hands and came back to Berlin saying that now this is how it should be done. And that sort of changed the attitude, at least on the surface, of the German meteorological community. But still, they sent man Thomas Schumann to be a consultant for 1 year, and he was accompanied by a colleague, Peter Emmerich, and both happened to be from former DDR. And other people I know who are from former DDR are very good and progressive. So something is happening in Germany, but the attitude before was absolutely ridiculous. So that was a great problem, that the biggest country in Europe had this attitude. Now, and partly it's because I also, when I was a forecaster in southern Sweden, I had to brief people going to Germany, flying. And the TAFs, the aviation forecast from Germany, were enormously long and tedious. And so either you have to try to understand what is German forecast, because of all kind of probabilities and trend and whatever in that forecast. You either had to understand what he meant, or read the whole forecast for the pilot. So it was pain in the neck with this German aviation forecast. And then I also learned that for longer forecast, the Germans had a rule that if their model agrees with IdroMeteoClima, they follow IdroMeteoClima. If they disagree, they follow their own model, or vice versa. But I have some very clear rules, very deterministic. So I asked a German colleague, which I couldn't offend too much, how come that when it's short forecast, you are extremely probabilistic, but beyond 18 hours, you are extremely deterministic? They said, well, a German forecaster tried to survive his shift. So if now there's a combination of lightning, fog, and snow, and the plane drops down, and it's not mentioned as a probability, he is in trouble. So a German forecaster is sort of to survive by putting in probabilities for what, but then after 18 hours, he has a clear rule dictated by the agreement between the German model and the European model. So, so this is a caricature. Unfortunately, it was a real, I think there is progress done now, of this picture I made a long time ago about the blame game culture. So first we have the public, that the forecasters misled me. I am not to blame. Then the forecasters say, well, the NWP, the computer, misled me. So he's not guilty either. The modelers then say, well, there was some observations over Canada or a ship in the Atlantic that caused this bad forecast. And then the scientists say, well, the atmosphere is chaotic. It's wonderful. Nobody is at blame as long as they blindly follow the deterministic forecast. Where I would like to see the opposite, how the scientists say that, yes, the atmosphere is chaotic. That is true. And just because of that, we have an ensemble system taking this into account. And then the forecasters say that we don't promise more than we can stand for. We have an honest attitude to the customer and tells him even if we are not certain. And the customer say, well, we base our decisions on the available information. So
that is very nice.
So this is a change of attitude. But this is what I put down some days ago. They're still in the methodological community, perhaps because we are too much educated in the Newtonian tradition. So they have the politically incorrect methodologies, in particular from Germany. But they might have changed now since the finance ministry had given them orders that I don't like probabilities. Then we have the politically correct methodologies who says that, who thinks in his mind, I don't like it either. But he says that it's a wonderful thing, it will be revolutionary, and all forecasts will be presented in probabilities. And Roberto Brizza will be presented, we love him. And he will have a career because he feels safe. Because if all forecasts are in probabilities, nobody will like it, it will be a completely mistake. But he has said the right thing. Then I want to put myself as a sort of the practical forecaster. Yes, I base my forecast a lot on the ensemble information. And I take that seriously, probably. But I do not necessarily then mention the P word or bring out numbers, unless it's sort of a best way to communicate. And I will now show at least 7 ways how to communicate uncertainty, based on probabilities perhaps, but not necessarily dealing with mathematics, if that is not the optimum way. So there is sort of 7 ways to communicate probabilities from my experience. Yes, you know, there was a man on the sky that, I'll come to that.
Poker face. God, I like.
So, and this is a true story. I was on holiday in England in summer 75. Then you could just go up to Bracknell and be introduced and see the Met Service. And I did that. Then when I was on my way out, I told my host, by the way, I always understand your Radio 4, the popular, you know, where they play pop music and weather forecast. I only understand and remember your Radio 4 forecast, and they seem to be quite good. But I never understand or remember the Swedish Program 3 forecast. Well, he said, I don't know what you're doing in Sweden, but in England we have a rule at the Met Office that this type of forecast should not exceed 30 or 35 words. 30 or 35 words. And that sort of is an effective filter to concentrate on the most essential parts. But that is wonderful. It was the first time I encountered this problem. So I went back to Sweden, and on my first shift when I had to make a Program 3 forecast, I made it only 30 or 35 words. And all hell broke out. because I had not mentioned the rain shower in northern Lapland's mountains or the fog in an island or in the Baltic Sea. I was really in trouble. But then, like a sort of American Hollywood movie, Robert Redford is sort of in trouble. the cavalry comes. And the red phone rang. The red phone to the control center in Stockholm, the radio control center. They phoned down to Norrköping just to thank SMHI for an unusually nice Program 3 forecast. So I was saved by this telephone call. Now, if now the methodological community had been a normal community, all these people were, perhaps Anders has a point. Perhaps we should try this and see if it works. Because after all, there was a customer response. No. I knew that unless the control central in Stockholm rang both before and after I issued my 35-word forecast, I would be in trouble. So there was no reaction to this in the methodological community. It continued with this culture of predicting as much detail as possible. And that was, in my view, it's still now when we put out on the web all kind of 5.3 millimeter forecast of rain. So filtering away less predictable and less important information makes the forecast easier to understand and remember. And it will also appear more consistent from one broadcast to the next and increase the trust. And it will also verify better where sort of unpredictable details have been removed. And the probability aspect here is that what has been left out are sort of less important events with low probability. If now there is really a risk of an important event with some probability, that can then be covered within the 35 words. But most of these things can be in a Radio 3 or Radio 4 forecast left out. So that is the first level of dealing with probabilities. You filter less relevant. Then in Sweden, I have a colleague who has a private Met service, klart.se. And he sometimes makes sort of pedagogical experiments in real time. So he put out an ensemble forecast by his own making, looking at different, both NCEP and WF data, on his web. So everybody could day by day follow how the observations verified this forecast. And he said that it's an 85% spread, so 85% of the observations should fall in this sort of shaded zone. So day by day, people could see how the observations fairly, almost too well, followed the forecast. And they were highly impressed. And they even said, well, you must be cheating. You must have known beforehand that this was a favorable event. So I had to intervene on the blog and said, well, if Martin knew that in advance, he would not be here, he would be living on Bermuda, because that is even more difficult. So it is just a normal practice in ensemble probability forecasting that Martin has shown, and it's open for any Met service to have this once a while in real time to show people. Here is another example where I was not happy about that. He was uncertain. It's called a bifurcation or a bimodal development. The weather can take two ways, and I was nervous that it would go in between, because that would be difficult to explain. So now this is what happened. He had a bad start because of some clouds that didn't resolve or whatever, but then the forecast became quite good, and it went down to the cold version, then jumped to the other one, and people got the message. It was a bimodal situation, but in this case at least the verification was not in between, it was in either of these two. Then we have in the literature, and I rely again much on the books, Kahneman's, for example, called the framing effect. And it has turned out that a small risk of rain or a high chance of sunshine or dry is interpreted differently by people, although it's logically, mathematically identical statements. So we have an example of this, is a bottle half full or half empty. So, and that can be used if you want really, without inflating your probabilities or your, like Crick and people in California. You can, without sort of scientifically lying, choose to say there is a risk of rain or there is a great chance of dry weather, depending on who you are talking to. Then there are, it so happened that one summer there was a risk of severe thunderstorms, even tornadoes in central England. And a lot of councils in central England, for example Birmingham, were told about a small risk of this. And they did not react. It turned out that if, instead of having small risk or small locations, they have said there's a great risk in Midlands. Because, as I said yesterday, if you increase the area or increase the time period, the probabilities automatically, mathematically, will take higher values, but still be consistent with smaller values for smaller periods or smaller. So, but it will have a greater psychological effect. But still, you are not cheating scientifically. Then another example from reality is a case from a flooding in Sweden in 2004. And here is the meteorologist. Here is the rainfall, the final rainfall. And the meteorologist, unfortunately, followed the European Centre forecast blindly. So 4 days in advance, they warned about heavy rain in central part of the region, which turned out to be a good forecast. But of course, nobody knew that at the time. Because next day, they warned about heavy flooding or heavy rain to the northwest, because that is where the European Centre had its rain on that day. 2 days before the event, it was to the southeast. Then 1 day before, they were back where it actually then rained. And I used to ask people in Sweden, now, how good were these forecasts? Well, half of them were good and half were wrong. No, I said all were wrong. Because first of all, the first one that actually turned out to be good, you don't really trust an extreme forecast deterministically 4 days ahead. And all the other ones jumped all over the place, so even the last one could not be relied on just because the general impression is of great uncertainty, so all forecasts were bad. The hydrologists at SMHI did something different. They also had started a weather service, and they relied, it was before the nice weather service they have now, so they relied on maps from the European Centre, so they had some idea about probabilities. But what they did was this. On the first 4 days ahead, they said somewhere in southern Sweden there will be heavy rain. So all the agencies were put on some sort of alert. Then next day they more or less repeated, slightly they excluded the extreme south, that in 3 days' time there will be heavy rain somewhere. And then they narrowed in. 2 days before, they more or less had the right area, some over forecasting around. And then finally 1 day before, which was the useful time limit, they more or less had the same forecast as the meteorologist, with the difference now that people who got this forecast believed in it. It was zooming in. So it gave confidence in the last statement. So sort of the sense morale that don't promise more than you can honor. And that was the policy the hydrologist at the Swedish Met Service followed. Now we come to the body language. Because if you are on TV or perhaps even radio. You can use your voice or your body to, as we all do when we talk, scratch your nose or play different tricks to give a sort of impression of that we are not quite certain. So here we have, I can't remember his name just now, but he was famous for having a very good body language. And also by, I mean, depending on what you show and you look worried about storms in the Scottish Alps. Or here you have a Finnish lady who is, instead of 80% risk of thunderstorms, that you would be lucky if you escaped a thunderstorm. So you convey by sort of human this 80% without mentioning the P word. Then we have what I found impressed on me is when the forecaster tells a story. And I remember a forecaster at the BBC in the 80s, Bill Giles, which you might remember. Once in a summer broadcast, there was a low brewing over the Bay of Biscay. And he said, well, this low is likely to come in over northern France. But I have seen this before, and I wouldn't be surprised if it takes a slightly more northerly route in over southern England. But as it looks now, northern France is more likely. And I was very impressed, because what he did, he expressed his uncertainty by mobilizing his experience, his knowledge. He has seen these storms, and he sort of conveyed this experience in a way that impressed on me. Aha, he's a clever guy. Much more than if he had said, well, the storm will go to northern France, full stop. So, for example, if you have a problem with if it will be cold or not, it can either be cold air from Greenland, which you could tell might arrive, but storms or low pressure systems over Britain might stop it, as it looks now, but we can't be sure. Or in a more mesoscale, that low clouds might break up due to certain factors, or the cold air might stay. So you give a background to the scenario, and then you can put in sort of uncertainty without people really noticing it. But never blame the computer. Neither before the forecast or after the forecast. I have seen terrible examples. Well, we don't know the weather because the American model says cold weather, the European model warm, and the Met Office in between. Then you are more or less handing out the maps to the public. Choose the one you want. Or afterwards, or if you said that the forecast has been jumpy. Yesterday it was cold, the day before it was warm, and now it's in between. We don't know. Then you appear helpless. Everybody knows that you have a computer, but you should take responsibility yourself for the forecast and phrase the uncertainty in a more clever way. And also after the event, don't blame the computer that you as I had in this blame game. Take the forecast as your responsibility. Because you'll never blame the radar or the satellites for bad 3-hour forecast of rain, for example. And it was it was my last week before I retired. So it was a gift from the Met Office, I felt, BBC and the Met Office, to me, because I had been at the Met Office for 2 years and I had taken part in meetings and discussions about how to deal with uncertainty. And what happened now in mid-December 2011 was, in my view, a perfect illustration to what we had discussed, and I was extremely pleased, and so was also the rest of the population. So not only my English, French were highly impressed, also the government and the board of the BBC praised what the forecaster had done. And when you think about it, as I will show, they were completely in the black. They hadn't got a clue what would happen. Because it was one of these situations where you haven't got a clue what the weather will be. But they acted very professionally. So I will give some glimpses. The problem was the following, that it had been a very stormy autumn. Now it was mid-December, and the models first had a low coming in over Scotland. Next day, the low was coming in over France, the storm. Following day, it was over southern England, and then it was again Scotland. And that continued actually almost to the day D, that the computer on different days had a storm at different positions. And it was not clear it was not clear, will it be storm? Will it be rain? Will it be snow? Everything was on the table, depending on where the low would exactly come in. So the meteorologist never blamed the computer's jumpiness. So Carol Kirkwood, the chief forecaster on the BBC, said at one that the cyclone has changed track, and we have revised our calculations, which is scientifically rubbish because the cyclone has not changed its track. And when we revise our calculation, it's not that we take up a paper and pen and start to rub out and then start to but it doesn't matter, because it was that we are responsible. We are dealing with a very difficult law who is constantly changing its track. But we are doing our best, like more or less like in wartime. An enemy airplane is approaching and will bomb my city or the next city, and we are following it and it's changing its track. So they didn't fall for this temptation to blame a jumpy computer. And secondly, they normally showed very nice isobaric maps, or isobars, and they never did that, because that would have revealed the whole jumpiness. So what they had was a dark cloud coming. A dark cloud that some terrible weather will strike on Thursday or Friday. But then exactly what it would be was sort of left more in the shade. But still, in a professional way, that something terrible will happen, but tune in our next broadcast, that then we might have more details about what will happen. And everybody understands that in all professions you have difficult days. And now it was difficult days for the forecasters. But they did their best. That is what they conveyed. They also, in the final days, had sort of scenarios, and again bring the people into the story, tell what the problem is, and people can understand that it's important exactly if it goes north or south of London, how the weather will be in this important town. So, and it was a success. Although people never was told what would happen. In the end, the storm went down to France and killed some people. So people know that something after all, but there was no much snow and not much flooding, so actually nothing happened over Britain. But still people were highly impressed by the performance of this, just because of their ability to convey the uncertainty in a professional way. That sort of increased their standing. So avoid categorical deterministic forecast. And don't fool yourself and others by this, and rather acknowledge it and show your skill, because it's in uncertain situations where the forecaster can show his skill and experience. If it's absolutely certain, then there is nothing to say. But it's in this, like the Bill Giles with the low over the Bay of Biscay. With this uncertainty, he had an opportunity to show his skill and experience. And then be in control. There's a debate in Britain about should they use the word uncertain. I don't have any strong views about that. I sometimes said, yes, it's a difficult situation. So when the computers are jumpy or do not agree, it's a sign that the situation is difficult to forecast. That is my recommendation of using words. And then, as I said, bring in people in the picture. as much as possible without being boring or long-winding. Tell them what is happening, what the problem is, and then they will appreciate that and also get indirectly some feeling for the uncertainty. And after this, I had left Britain by then, but there was another case some month later of another character. It was east winds, cold east winds, and mild west winds. It was not quite certain where they would meet. Of course, that is very important if it be +8 or -2. So they had a similar case, and I got these pictures from Peter Gibbs, one of the forecasters, and what they did, among other things, was to put out this picture that depending on where this borderline will end up, it will either be warm or it will be cold. And as far as I understand, people were quite happy with this type of broadcast. That the situation is difficult, we are working hard, and this is what we can tell. Then we have Causal Probabilistic. And as I mentioned in my Tuesday lecture about confidence intervals, the frequency statisticians talk about confidence intervals. The probability 80% is that the confidence interval will cover the truth. Whereas the Bayesians have the credible intervals, 80% that the truth will be in the interval. Are you with me, Stefano? So to have this Bayesian and frequentist quite opposite definitions of intervals actually can provide some ideas for us. Because the frequentist approach would be that we assume some sort of tacit 70% probability. So that is our fixed value. Whatever we say is 70% likely. And then we provide, and I think that is what most people think, that when we say something, it's not 100% certain, not 50-50, either somewhere in between 70-80%. So it's not far away from people's intuitive feeling. So when we say 25 to 29, or 27 plus minus 2, it's sort of underlying 70% probability, or 10 to 20 millimeter rain, or 6 to 12 meter per second wind, assuming implicit 70% probability. In this case, I might favor personally the frequentist approach, not the Bayesian, because the Bayesian would be that we have a fixed interval. And then we state a probability that the truth will fall in that. And then we have the problem that we have to specify both the probability and the interval. So it involves more numbers. So, but sort of both these are possibilities that you are not talking about probabilities. You talk about probabilities in relation to intervals. So either the frequentist with a fixed probability and the interval is specified, or the Bayesian, as I understand it, would involve both stating the probability and what interval that refers to. Yes. So it might be too much numbers in the Bayesian approach, but there might be some other clever solution to the Bayesian approach. The Met Office has, of course, a probability approach by their impact matrix. So the x-axis is proportional to the probability, and the y-axis the impact in some loose, or is it the opposite? Sorry, the probability is on the x-axis and the impact on the probability on the y-axis and the impact on the x-axis. So it means that yellow is both for low probability of an important impact or high probability of a less severe impact. So they try to combine impact, consequence, and probability. It has been criticized that it's not possible to verify. That is quite true, but the purpose is not always to verify, it's to sort of, as we come back to with the EFI, a sort of alarm bell. So the public will be given the color and then find out in the Met Office website exactly what is going on. It cannot be...
You could verify by substituting the y-axis with frequency.
With
frequency. Observed frequency.
Yes, but the x-axis, I mean, impact can be quite, it's rather loosely, because impact is not strictly defined.
Impact is a mixed concept. Some meteorology, some other...
Yes, and then also you have another problem as between Sweden and Italy. The impact of 2 centimeters snow.
It's totally different.
Yes, and the same for...
New York and in Washington.
So,
well, no.
yes, and also between England and Scotland. So this should not be over-interpreted. It's just a sort of a signal bell, an alarm bell, that something needs to be looked at. And then odds. And as far as I remember these investigations, you would assume that the British, who are playing on horses or whatever, in terms of odds, would favor odds also in weather forecasting. But I haven't found any strong signal from the investigations that the British, for example, would favor probabilities in odds. But it is a possibility to do that. It's a mathematical possibility to convey uncertainty. Then the importance of base rate. And I have a funny story. I was in London, a rainy day, on the bus, and there were 2 nice ladies, and they were chatting Portuguese. And when our eyes met, I said to them, "Aha, you are speaking Portuguese." They were very happy because me, as they thought an Englishman, could recognize their language. And then I made the crucial mistake. I said, you Portuguese must find the weather here in England rather awful, you know. So what mistake did I do? I actually broke one of my holy rules about base rate. I've been preaching about base rate for 2-3 years. Then I commit this error myself on a bus in London. I forgot the base rate. Anybody?
You were Brazilian.
Yes. There are 10 times more Brazilians in the world than Portuguese. So I should have realized that the chance of them, although Portugal is a member of the EU and closer to London than Brazil, there are at least 10 times more Brazilians around. And they are not poor, so they can also travel. So I should have assumed a priori they were more likely to be Brazilians than Portuguese. Then somebody else, a Brazilian, told me, just because it sounded like Portuguese, it must be from Brazil. Because when Portuguese speak Portuguese, it sounds like Russian or Czech.
Not only, but in Portugal it rains a lot. In Brazil, well, it depends. Also.
Well, it's, yes. I didn't ask them from where in Brazil they were. So the importance of base rate. And people quite frequently forget that, as I did, like the bus. And if we reference our probabilities to the base rate, in our case is a climatology, we can achieve a lot. So, for example, now this 50%. Well, first of all, if there is a 2% chance of some tornado, you will then make the message more forceful, but it's 20 times more likely than normal. Then you use the base rate, the climatology of tornadoes, which might be very low. So even if the risk is low, it's 20 times higher than normal. Now, the 50%, we discussed that before, is a problematic probability because people take it for 50-50. You don't know, you are left in the dark. But again, it depends on the base rate. So tossing a coin, then it's true. Then 50-50 is I don't know, because the base rate is 50%. But if you come to snowfall in Rome, 50%, is as I understand, a very strong signal, because the base rate for snowfall in Rome is very low. Or about sunshine in Rome, 50%, is also a bit out of the normal, because Rome, as I know it, is a very sunny place, at least in summertime. So it all depends. It is 50% depends on the base rate, what we are comparing with. So it's 50% for the coin, perhaps 2% for snowfall, and 80% for sunshine. So the 50% should not be a problem, except when tossing a coin, if you keep the base rate. And again, if you have problem with a 50% misunderstanding, you can say it's much more likely than normal, or 25 times more likely than normal, or much more likely than normal. So you refer to the normal probability. And the European Center Extreme Forecast Index is a sort of take the base rate into account by comparing the probabilities with the climatological probabilities. So here you have this base rate set into mathematics, and again, it's not probabilities, it's a degree of extremity the EFI measures. I will come back to that. And then you have probability numbers. But as I said, probability numbers is just the last and the seventh of possibilities to convey uncertainty information. And so it's not just a matter of handing out numbers like that and leave people to do the best out of it. So coming back to this Birmingham tornado, instead of saying it's 10-15% for individual locations, you say it's 50 or 60% for the region as a whole. It's mathematically consistent, but the psychological message becomes stronger. People, somewhere perhaps we should do something. And I also recently read an American trick from the 50s when they made seasonal forecast. So here you have a bell curve of something, for example, temperature, and you divide that into 3 equal parts, as the Americans did with the temperature for a monthly or seasonal forecasting. And the normal part is always 33%. This might be slightly violating some mathematical laws, but I think within the limits of usefulness. Because when they then issue a forecast, the normal class is always 33%. And then if it's now in this case bias, or you expect a warmer than normal, then what you issue is a 67, in this case, 50%. 50% probability for warmer than normal. And since normal is always 33, the probability for cold is 17. So you can actually, and as the Americans did, plot maps with the probabilities, only one value. And then you could, with some not too difficult mathematics, understand the risk of normal always 33 and colder, in this case, 17. I don't think it's mathematically consistent, but within the limits of usefulness, it's a clever way to simplify the problem. So this is the value they actually then published. So that's it. Thank you. I just add something that came to my mind from this about base rate, which I did discuss. You remember it's 100 years or a little more since the First World War started, the First World War in 1914. And you might remember that it has always been written as said it was an unusually warm summer, a warm, beautiful summer that ended in this catastrophic war. And now scientists at Météo France, climatologists, had found that yes, it was an unusually warm summer for that time, early 1900s. But actually, according to the typical climate now, the summer 1914 was unusually cold. So again, it's important to keep the base rate into mind. Now, this lecture now about probability products was first thought to be the first one I should present. But then in the early morning hours, I thought that it might not be that important as the others, so I put it at the end. And it will be more some personal reflections on what I think about different products, and it should not be taken too seriously, because I'm not updated in perhaps improvements, and sometimes it seems I was a forecaster, so it does some personal reflections. And this here we have the stamp map, and some forecasters still want to look at them, to look at the individual forecast, and some hope to find out which one should we trust, which one is the best one. Now we come back to that tomorrow, why that might be fruitless or almost impossible. Then this is now the original clustering. The clustering we started with in 92 had the aim of putting together members that were similar. And we used the 500 hectopascal because it showed the large-scale evolution. So similar members in some sense were put together. And it also tried to distinguish between sort of different synoptic evolutions. So it was not a bad system. But whenever you make means, averages, as we discussed some days ago, you are likely to commit errors because you don't get anything for free. So on day 4, the first cluster is on day 4, 5, 6, 7, the last on day 7. And since the spread increases, you have a larger divergence among the members in the cluster on day 7. And that's why that cluster tends to look more smooth and more unrealistic than the clusters on day 4. And when we have many clusters, the first cluster might be very populated, many members, large spread still, and look more smooth, whereas the last cluster, the least populated cluster, perhaps only 3 members, looked very detailed just because of the few members. Now this is sort of unavoidable consequence of averaging, but the forecasters were annoyed because the maps didn't look like a real weather map. So the center has now changed, and in my view, my personal view, to the worst. They have more or less a similar, well, not in detail, but they have now this cluster principle where they group together forecasts which are similar. But then instead of presenting a cluster average, which then might look unnatural, but bring out what is common in the forecast, they try to find, always find, what they call the most typical member. And then I think the center is scientifically on weak ice. Because as I will talk about tomorrow, and what is also stressed in many of these books, Kahneman's and others, it's a common mistake to confuse what is typical and probable. So it is now, what you have here are members representing the cluster. And that's fine. But it's a member with all its wonderful synoptic details, which is typical for a weather situation. But these details might not always be what is predictable, what is said to be predictable in the cluster. So it's an attempt from what I see as an attempt to still stay in the deterministic forecasting. And in some sense appeals to this notion that to find the best member, because of course the member representing cluster 1 can then be seen as the most likely member, if you want. But again, if there are many clusters, even the largest cluster might occupy or represent a minority of the forecast members. So I'm not quite happy with this new clustering. I think it's nice, what I call Steven Spielberg clustering, but it is not scientifically sound. Probability maps
you will not, for long times, it might have changed, but I'm not aware of that. Probability maps were only produced outside the tropics because there were and perhaps still is some rather marked systematic errors in the tropics. So the probability maps would be misleading. And here is now typical for rainfall, and another one for gusty winds. And it's taken some days before this bad weather hit the Mediterranean with snowfall in Italy, etc. And they are quite useful. And I think that what this trainee I mentioned was working on was to combine these two maps into one map of probability of rain and gusty winds at the same time. And I still think that that would be a nice product, but it has to be made by going into the database and then grid point per grid point decide if these two conditions are fulfilled and then compute probabilities accordingly. It cannot be easily deduced just by looking at the maps. EPS-grams, I think most of you are familiar. There are only some points I want to make. One is, and this is a presentation I had in Hong Kong, but since the EPS-gram for Hong Kong is rather typical when it is wrong, or well, not when it's wrong, but when there are sort of conceptual problems, I still keep it. So, for example, in the cloud forecast here, in the first forecast, but just by a quick look, it could equally well be 0 octas as 8 octas, because absence of any blue column could mean both 8 octas or 0 octas. But now I think for continuity we realize that it is 8 octas. But formally it is not quite true. Then another thing that when I left Sweden, I looked at the EPS-gram for my town, Uppsala, and found some heavy staples for precipitation. And I had promised my wife that in my absence there will be no snow for her to shovel. Now there were big staples in the EPS-gram for Uppsala. So I was taken back. But then I forgot to look at the y-axis. The cloud y-axis is always from 0 to 8. But the y-axis is for the rest are adjusted to the variance of the forecast itself. And what was forecasted for Uppsala was precipitation between 0 and 0.3 millimeter. So these staples reflected heavy rainfall of the 0.2 millimeter size. So I could live happily. And the same is true for the wind speed and the temperature. But normally when you misread is the precipitation, where you might see, as I saw, new staples and believe that there is a heavy rain coming. Always look at the left-hand y-axis. There are, not in this case, but if there are some extreme values, they will not inflate the y-axis, but put the number above in red. So that they will still keep a fairly decent, reasonable interval in the y-axis, and this sort of very high value will be put as a red number above. Then this also shows problems when, as you can see here, the blue line for the wind and temperature does not agree very well with the red line, the control, and the EPS as such. And that is something also to be observant about, because that reflects that the grid points are not identical. And now in this case with Hong Kong, where you know where it is, so the grid point, you have one EPS grid point over land north of Hong Kong. And then you have another one in the sea outside Hong Kong. And the system should pick out now the nearest land grid point. That is one to the north, but it might be on a hilly terrain compared to the operational T1279, the state-of-the-art model, which happens to have the grid point more or less exactly over Hong Kong. That's why you have a discrepancy between the EPS and the operational model. It's something to watch out for. And on the ECNWF website, you can click and get maps like that. And it might be important in Italy to find out exactly where the grid points are to the location you are interested in. And here is a nice meteogram from Bologna. And why don't you extend it to 6 hours or it's quite nice. Yeah.
They are 6 hours. It's a different product, but it is on 6 hours. Not the box plot, but the meteograms are on 6 hours.
Yeah, but
The box.
then topicals, I think it was Federico who said that one of your favorite plots was this tropical cyclone, because it's also one of my favorite plots. Because normally the EPS goes up to 10 days, and in the previous it only starts to compute these plumes of the trajectories of tropical cyclones when a tropical cyclone has been observed and has given a name. But a very good invention now from European Center is to find out about the possibility of tropical storms forming. That can be done by looking at the divergence pattern or temperature anomalies. So they can early on, 15 days ahead, indicate a possibility of a tropical storm forming and then see how it is advected in the forecast. And this is what you get. And as far as I know from my WMO travels to Asia, when I have sort of looked at this more specifically, they are quite skillful, and you seem to agree. Of course, that they will not hit Bologna, but with this sort of globalization, you must still be interested to advise people going abroad. So they give early warnings about possible hurricanes or typhoons to exotic, and also in the Atlantic, because sometimes these tropical storms can turn extratropical and become very violent storms in our neighborhood. And then when they are formed, you also have this traditional, so to say, plume where it is heading. Then you have the tropical cyclone epsogram, and remember it's also following the storm. And it always disappoints me because the epsograms normally are not deep enough or intense enough. So I hope that this will improve with higher resolution, but still it's a useful tool. Then you can also look at ensemble mean maps and the variance of the pressure to spot where a tropical storm is developing. Then working with EPS, and I come back to this that the first product of the EPS is not the probabilities, it's the ensemble mean or median. It's the most robust and skillful product from the EPS. And the second one is the probabilities or the variance. But there are still controversies about the ensemble mean, because it, as a mean, does not always represent the physical possibility. But in my view, that is secondary. Here is an example from Holland, where they were planning to have an ice skating competition on the canals, and there was 30% probability for cold weather and 60-70 for mild. So they decided to cancel. But in the end, I think it was cold, but still they made the right decision. But as you can see, the ensemble mean goes in between these solutions. So in some sense, the ensemble mean cannot, not likely verify. It will be either or. But still, if you have the approach, as I sometimes find fruitful, the aim of a forecaster is not to be as right as possible, but to be as little wrong as possible. Then with this later approach, be as little wrong as possible, then the ensemble mean fits into the picture. And I think it was Roberto who showed that you can spatially filter fields and bring out more predictability. And that was what I was actually doing 30 years ago at the European Center. Here are now 6 forecasts, all verifying at the same time. And in full scale, all the details are there. But if you, and you can still see there are differences, jumpiness between, they all should verify at the same time. But if you put on your busy glasses, you can see that there are some common features in all of them, except perhaps the upper right. They all have a cyclone to the west and an anticyclonic to the southeast. And that comes out more clearly if you now look at in a T12, do you have the 12 largest spectral components? And that brings out the large-scale feature, and now these sort of similarities become more clear. And as I showed already in 1983, the skill of these fields are quite higher than the operational forecast. So it confirms what Roberto said the other day. And then what I think is a nice thing to do is to combine the ensemble mean as a background to different type of probabilities. And here is now for the same situation, all forecasts verify at the same time. So you can see not only consistency in the average flow pattern, the ensemble mean, but also in the probabilities. And it sort of brings back that when you make averages, you actually will both increase the accuracy and the steadiness, the robustness, you have less jumpy forecast. And that even applies to what we discussed over lunch, if you lag forecast. So here I have, I think, 3 or 4 European Center forecast. It is a high resolution forecast, verifying at the same time. So it means a 120-hour forecast from today, 132-hour forecast from yesterday, and 144 forecast 12 hours earlier. They all verify at the same time, and you average them, perhaps weighting them slightly. And then what you get, this sort of poor man's ensemble mean, is not only lowering slightly, so that the gray line here is the skill, the accuracy of the last ECWF forecast. The full gray line is the RMSE of the lagged average. A small but significant improvement. But what is sort of surprising, perhaps, is that the jumpiness decreases roughly 3 times more. And I know that from the Met Office, half of the complaints to the Met Office about bad forecast were actually about jumpy forecast, because people interpret a jumpy forecast as being bad, which of course is not quite true, but it gives an impression of badness. So if you bring down the jumpiness only, that will give a warm feeling to the hearts. They will feel more confident about the forecast, even if they are not terribly much more accurate. So bringing down the jumpiness by lagging or by preferably using the ensemble mean will give an impression of a huge improvement in quality. So, but the debate is still on about the ensemble mean, and one is that it doesn't display realistic flow patterns. Quite true, but it's only, I see, a problem for us methodological experts. And it cannot forecast extremes, yes, because we asked it not to forecast extremes unless all members agreed on this extreme. If only a fraction of the members have the extreme, the ensemble mean will not have any extreme, but we have a certain probability about this extreme. That is the whole point of averaging. What you average away, you put back consistently as a probability. And you could also say that 7 meters per second is not very sexy, so you sex it up by adding 30% probability for gale force. Then it becomes more exciting and more useful. And then the ensemble mean for different parameters might be inconsistent. You might have rain, ensemble mean rain, and you have 6 octas ensemble mean cloud. Of course, yes, this is a price we have to pay. On the other hand, we already have had for 30, 40 years inconsistency in the deterministic model between 6 or 12 hours accumulated rainfall and the cloud forecast at the beginning and the end of these intervals. They could very well have 1 octa at the verifying time 00 and 3 octas at the verifying 6 hours later, and in between a lot of clouds and heavy rainfall. So this inconsistency we had already lived with for 40 years and have been able to cope with. So this is not it is sort of a necessary price we have to pay for having more skillful and more robust weather forecast. But I'm sure the averaging can be done more skillful, in a more skillful way, so this sort of negative sides might not be so crucial. But what I will discuss tomorrow, it's I think a reflection of this misunderstanding between typical and probable. An ensemble mean is more likely to verify in individual points as a forecast, but it doesn't look typical. So a 10-day forecast with all its wonderful fronts looks typical, and it is typical, but it's not probable. And it's the same problem now with this new clustering. The new clustering with a selected member, then it looks typical, but it is not probable. And then here's a sequence I made for last time I was in Bologna. I showed this. So if you remember that, it is the ensemble mean. All these forecasts verify on the 11th of November. And it's the ensemble mean of the pressure, and overlaid are probabilities of rain and wind. And you have now a sort of disturbance, disturbed weather over the Mediterranean. And in the real forecast, the deterministic, there was jumpiness where this disturbance would end up. And as you can see now, this is a 7-day forecast. 6-day forecast, it becomes sharper. 5-day, it starts to slowly drift to the west. Day 4, and then day 3, which is more or less what then happened. So the 7-day ensemble mean was by no means perfect in position, but then the change was gradual and consistent, and much more agreeable than if it had been jumping around as it normally does in the deterministic forecast. The extreme forecast index Roberto talked a lot about. It just to remind you, it has become more or less a sort of a sub-science at the European Centre. But here you have 2 PDFs. And PDF is probability density functions. One is, so you have some temperature on the x-axis and the probability on the y-axis. And here you have the climatological L bell curve, the blue one. And then you have the ensemble bell curve in red. And then you can change, you can redefine it as you add and create 2 cumulative distribution functions like that. And if you take the derivative, the slope of these lines, you will get the first dashed line. So the largest, the steepest slope in these red and blue curves coincide with the peaks of the 2 bell curves So that is the mathematical relation. And then the EFI is in principle the area between these two. There's much more to say it, but it's not necessary in this context. And here is an example, also some days before the Bologna snowfall. And as far as I could see, you have good warnings about disturbed weather, not necessarily about snow, but a long time in advance about disturbed weather conditions in the Mediterranean. A very nice product, which I hope you have access to, is the clickable EFI map. So here you have, in the background of the ensemble mean, which gives the flow pattern in general terms, you have colored parts which tell you about high EFI, high extreme forecast index values for rainfall, temperature, and wind. And the legend is at the bottom. And it's very nice because it gives you some sort of snapshot of the situation. But remember, it's not supposed to go into detail. It's just a sort of alarm bell. Aha, it looks cooler than normal over Morocco and the Western Mediterranean, warmer than normal over Russia. And then you go into the ipsograms to really see what is going on. And these maps allow you to click on any location, and up will come either a normal EPS-gram, like the one above, or one with a modeled climate in the background. And that is very important. It's sort of this reference base rate concept. You can relate the forecast to what is normal. Since it's not it's a modeled climate, so the idea, as I think Roberto or you discussed, if the forecast is warmer than the model climate, we assume that the real weather will be warmer than the normal climate. It's not always true, but it's a good assumption. And then I will tell you more in detail tomorrow how you can interpret the relation between the forecast and the model climate to draw some clever solutions. Then finally, Tim Hewson has his own page with extratropical matters, also up to 15 days. And I also like that because he avoids going into details. He looks in different ways on the general the degree of disturbances in the atmospheric flow and plots that in different colors, so you can, in a more consistent way, see where the atmosphere is disturbed and where it's not, where there is sort of likelihood of high winds. And then from there on, go into the ipsograms and get more details. Thank you.